Hi, and thank you for attending to this webinar. My name is Nuno Almeida, and I am the application engineer for HP for the Benelux Nordics region. My job role consists in helping customers to adopt and improve their capacities with HP Multijet Fusion. 3D printing, and especially MGF, allows to rethink a new way of designing process, the fabrication, and the supply chain of parts. The freedom of thinking a product this way can, in some cases, disrupt the market, the fabrication, and the value for the end customer. Another very important topic for a successful usage of MGF is sharing knowledge regarding designs and application possibilities to facilitate and encourage this transformation. With that goal in mind, HP creates regular DFAMs and webinars to give a state of art in the technology and applications. Today's webinar covers a very important segment for HP 3D printing in the area of healthcare, more specifically orthotics and prosthetics. Our agenda for today will start by making a brief introduction on the market and some notions regarding orthotics and prosthetics, followed by a 3D printing opportunity and the value proposition of MGF. Then a brief explanation on how technology works and the workflows associated with it. And finally, some customer success stories. As an introduction, I would like to give you some overview regarding the market and some notions about orthotics and prosthetics. If we look at the global healthcare market, we are currently talking about a market size of 8.7 trillion US dollars. In parallel, approximately 11.5% of the total population is over 65 years. Above all, it can be deduced that the increase of average life expectancy is being fueled massively by the use of new technologies in healthcare. Directly from 3D printing, we currently have a market size of just under 1 billion in the healthcare 3D environment, from hearing aids to prosthesis. If you look at the next few years, according to currently studies, annual growth of just over 18% is currently expected. So we speak of almost fourfold increase in the market size for 3D environment in the next 5 years. So there is enormous potential for business opportunities. Looking specifically for orthotics and prosthetics, there is a very large market that's worth almost 10 billion US dollars. Here it can be said that orthotic sectors in particular worth $6.2 billion in sales and accounts for more than 2/3 of the orthotics and prosthetics market. The top three types of orthoses are knee orthoses with 24% of market share, orthotics of the lower extremities like lower legs, and foot orthoses with 70% and 18% respectively. But what is an orthotic device? It can be defined as a support brace or splint used to support, align, prevent, or correct the function of movable parts of the body. There are basically two big groups in the orthotics world. Customized orthotics that are tailored manufacturing and are prescribed by a certified specialist, orthotist or podiatrist. Traditionally, they are handmade with carbon fiber or vacuum forming. The price can range from $300 to $5,000. The other kind of orthotics are the non-customized ones. They are inexpensive, mass-produced with using molds, can be bought off the shelf, some can be adapted. They can cost from $10 to $250 and they can be found on pharmacies and retail stores. Generally, the orthotic devices are used by persons with injuries or disease, and they are fabricated in thermoplastics or carbon fiber. Another important subsegment of orthotics are insoles. Insoles are for orthotics devices that support and correct an irregular walking pattern. They restore limb alignment and the positioning of the foot. Insoles can also be bought as customized insoles prescribed by a specialist, with prices ranging from $100 to $500. The traditional are fabricated through vacuum forming or CNC. Lately, there is a growth in 3D printing. Generally, these tailor insoles can only be ordered through a clinic. Another more affordable type of insoles are the prefabricated ones that can be bought off the shelf with a price range of $8 to $85. They are fabricated by injecting molding, and the level of customization is reduced. Generally, the customized orthotics insoles are used by persons with medical needs or by sport persons, and they are fabricated as rigid PP or PA and soft as TPU or EVA. Customizing soles are the correct specialized way of delivering treatment for the patients. Although more expensive, they are the ones that can better address the needs of the consumers. The market for personalizing soles is growing. The main key factors for that growth of demand in many medical users are aged population. The continuous increase of average life expectancy makes this older population having special needs regarding feet comfort. Obesity, the proportion of population with obesity continues increasing, and persons with higher corporal mass tend to have problems in their feet due to the support of the weight in the base of the foot. Diabetes is also another big problem. The way of living and eating and are contributing to a continuous increase in diabetes. This disease generally creates feet health problems that need to be addressed with customized insoles. By other side, the support customized insoles have seen a growth in demand due to number of persons running as part of a healthier way of life. These persons look for comfort in their feet while practicing their sports. Intensity of the sports in high competition, the athletes are every time more exposed to intensive trainings and hard practices. This affects particularly the feet that in most of the sports are crucial for a good performance. The market have nowadays a value of around $700 million and is expected to grow by 7% a year, which is a higher rate than the growth of the out-of-shelf insoles. The other big group of focus in this webinar are prosthetic implants. Prosthetics or prostheses are artificial devices used to replace a missing body or part. This can be due to birth defect, injuries, or diseases. 80% of the amputations are of lower limb. The prosthetic socket is the most important part of a prosthesis. The socket is the part that contacts with the residuum of the limb. The design of the socket needs to be fully customized and special needs to study the biometrics and the dynamics of the patient in order to correctly design the part. The socket is traditionally manufactured by vacuum forming, CNC, and carbon fiber layups. Generally, the price range can go from $800 to $1,500. An interesting application that was unlocked by 3D printing are fairings. Basically, they are cosmetic elements that help to hide prosthetic itself, having a positive impact on the ability of the users to embrace their disability. A full prosthetic can range from $10,000 to $17,000, depending on the components. The total market of customized orthotics and prosthetics is estimated to be around $3.2 billion and is expected to grow around 7% a year. Like the insoles, there is several trends happening in the personalized orthotics and prosthetics. These are contributing to a higher number of amputations and orthotic needs. The growth of prosthetics and orthotics have been focused on customizing by seeing the increase of these products. 80% of the amputations are lower limb and 80% of the orthotics are foot, ankle, knee. This product requires a high level of customization to be effective. By other side, the increase of demand is creating a gap of specialized workforce. Another characteristic of the market nowadays is that while there is a continuous industry consolidation of the main players leading to market monopolies, there is also new startups interested in implementing new ways of doing things with special focus on applying new technology on developing of a product. Jumping now to what can be the opportunity of 3D printing in this sector, we will cover now how 3D printing can be having value in most of this application. After presenting the market, it's time to define the 3D printing opportunity and the value proposition that HP MGF can deliver to this segment. There are several ways to justify 3D printing for our end user parts. The level of personalization offered by 3D printing is unique. The capacity of delivering unique geometries with medical supervision is the best way to adapt to the specific needs of the customer. By other side, the effective cost per part allows to bring some applications to the range of prices delivered by some of the off-shelf products or reduce the overall price on customized products. The way of manufacturing also changed dramatically, contributing to a faster and more sustainable product with less waste and no fabrication setup. Another advantage is that the supply chain and the scalability of the business can be adapted to the demand. 3D printing has been for more than 20 years in the healthcare system. There have been a wide variety of applications covering literally from head to the toes. There is also an increased trend on making these products not only effective, but also aesthetically appealing in order to help the user to deal with their disability. Basically, we can resume some of the most important and successful applications on 3D printing world as shown in the slide. Orthotic insoles, orthotic braces, cranial orthoses, prosthetic sockets, and prosthetic fairings are all ideal candidates to be printed. The criteria to choose fabricate these products in 3D printing might rely on size, volume, complexity to manufacture manually, and quantities. We now take a look over the most common fabrication processes used in this segment. Manual fabrication of personalized insoles basically starts with making plaster molds out of the foot and then making the insole by vacuum forming. The process is highly manual. Another method is scanning the feet of the patient and then CNC the insole, generally in proper polypropylene with a huge amount of known used material remaining. Some manual finishing is still needed. 3D printing is the most digital insole fabrication method and starts with the scanning and the 3D manipulation of the feet geometry. The fabrication is done in one step and dozens of different insoles can be produced at the same time. The only step extra is cleaning the parts and apply the cushion over them. Similar fabrication methods are used for general personalized orthotics, but with higher degree of complexity. To fabricate orthotics in a manual way, the process starts with making a plaster mold, followed by the creation of a part by heat molding PP, or by applying carbon fiber layups. The part needs to be finished with manual work, and this process is basically human dependent, and a person needs to be dedicated to this. In a SMID digital fabrication, the process starts with the 3D scanning of the part of the body needing the orthotics. The 3D object generated by the scanner is then manipulated in a dedicated software, and a CNC furon block is shaped in order to top work as a mold for creating the part as in the manual process. In a digital fabrication method, the process starts with the 3D scanning also and the 3D geometry manipulation. The fabrication method is fully automated and the human intervention is resumed again to unpacking and cleaning the parts. The fabrication process for the prosthetics follow the same procedures as in the orthotics, but what is important also to show and to better understand the supply chains in this segment, we can take a look to this slide. Generally, the process starts with a clinician or a podiatrist that diagnoses and prescribes the product. However, in most of the cases, they don't have fabrication capabilities and they rely on central fabs specialized in specific products. At the same time, you have OEMs that fabricate standard components or materials to build custom devices that supplies the central fabs. CAD and CAM softwares and scanners are also part of the supply chain, and names like Vorum or Rodin 4D are major players in the market. Generally, they are used by both clinicians and central fabs. As already mentioned, there are startups that are pushing the market to change this supply chain by having more efficient business models with more direct and fast relation with the clinician and the final customer. These companies can rely on service bureaus or central fabs if these ones have capacity on 3D printing. There is also a trend of this business adopting the technology in-house, and with that, they can deliver the final product without almost no interaction of third parties. It's in this business model that 3D printing have a huge potential to deliver customized final parts. After seeing some of the key aspects related with orthotics and prosthetics segment, the question is why produce 3D printing and what the main reasons for the adoption. From the manufacturer's perspective, there is a huge reduction of manual labor. With 3D printing, the manufacturer can ensure consistent repeatability and higher accuracy. It's also easier and safer to scale up the business. The clinicians, by other side, can have much faster turnaround on their patients with less fitting adjustments and with shorter workflows. The patients are extremely benefit by having better fits, lighter and breathable devices. The devices are more comfortable and they need less adjustments. What can then HP deliver? HP MGF can deliver productivity, store patient data devices specs digital is easily to retrieve them and repeat them, up to 8 times reduction of the manual labor, all-in-one solutions optimize storage space for solutions and materials, and up to 10 times faster 3D printing comparing to other technologies in this segment. 3D printing, HP is also a modular solution, which have direct advantages. By other side, HP also offers superior consistency and quality. The isotropic properties, the mechanical properties, the ability to design with the correct and precise adjustment to the patients. And plus, we have biocompatibility certifications that can be very important in this segment, especially the skin contact. HP is also offering a sustainable method of dealing with this industry that is a highly known industry producing waste. In some cases in insoles, more than 90% of the raw material is taken as non-used material. And so it's a huge problem to solve. By the side, P11, it's a renewable raw material that comes from natural sources and is not oil-based. So all these factors are very important to see the global picture and how can MGF contribute to disrupt industry that has not been changing for many years. And taking into account that to bring one of these applications to the market, generally you need to focus on size, volume, complexity of the part, and basically there are some that are more attractive than others. The values that I present in here regarding cost are just reference values. In common practice, you should request TCO from the application engineer for your region. However, we in the range of $6 to $12 and 20 parts being produced at the same time. And as you can see, you can produce a socket, for example, between $80 to $400, depending on the system that you use or the complexity of the part. These values are highly competitive. And just to illustrate that in a more clear way, you see that the margins of profit, if you target to sell your product at $1,200, your margins of profit can increase because your leading times to produce the time reduce. And we can also see that by using a more productive system, in this case the 5,210, you are able to bring the price product for half of the 4,200. These are very compelling reasons to adopt MGF. And I am sure that there's gonna be a continuous increasing of MGF in this segment because we have lots of sweet spots that can contribute to a disrupting way of doing things regarding orthotics and prosthetics. With that being said, it's time to make a brief covering over the MGF technology. Some of you might already been familiar with the technology. However, I will start with a brief explanation about how MGF works to put everyone on the same page. Multi-jet fusion is a powder-based technology, and the process can be divided in 4 steps. HP multi-jet fusion technology starts with a layer of powder material being spread on the printing bed. 2 agents then are used during this second step, a fusing agent and a detail agent. The fusing agent defines the area of the powder to be fused, and the detail agent is printed at the cross-section borders to avoid the thermal conduction to the surrounding powder, which helps to get a good part accuracy. After this, the powder bed is heated by infrared light. Water and other volatile components from the liquid agents evaporate, and the particles in these areas where the fusing agent has been deposited melt and fuse. This happens because the fusing agent is provoking more absorption of energy, and it has a higher absorption in a wider range of the wavelengths in the infrared region. And thanks to that, the temperature is higher than in the rest of the print zone, fusing the materials areas where the fusing agent is applied, while keeping the rest of the print zone with not fused material. A print layer with fused and unfused powder extracts along the z-axis to prepare for the next printing and curing cycle. The powder bed is recoated with a thin layer of thermoplastic particles. Once these fused layers cool down, they solidify and build the design 3D printed part. To better explain the process, I will let you with this video.
HP's multi-jet fusion technology produces quality, functional parts at a production speed which is up to 10 times faster than today's competing products. Unlike the slow point processes of some current technologies, HP's multi-jet fusion technology processes parts in 2 fast, area-wide passes to achieve top-speed part production. The process begins by applying a layer of material in a work area. In the opposite direction, in one continuous pass, we print fusing and detailing agents across the full working area. This pass combines the printing with the fusing energy, and the process is then completed. HP's proprietary architecture is capable of printing 30 million drops per second along every single inch of bed width, enabling extreme precision and dimensional accuracy. To produce truly functional parts, it's important to ensure that the material has been properly fused and that part edges are smooth and well-defined. To achieve part quality at speed, HP invented a multi-agent printing process. In this process, a fusing agent is applied on a material layer where the particles are meant to fuse together. A detailing agent is applied to modify fusing and create fine detail and smooth surfaces. The area is exposed to energy, and reactions between the agents and the material cause the material to selectively fuse together to form the part. The fusing process requires accurate temperature control across the entire material layer. HP Multi-Jet Fusion's closed-loop thermal control system does this by measuring temperatures at hundreds of points on the material bed. This information then determines which areas receive more energy to raise the temperature and which areas are cooled, allowing for control of thermal bleed and layer-to-layer fusing and cooling. The result is full control over mechanical properties, dimensional accuracy, and repeatability. The process is then repeated until a complete quality, truly functional part has been formed. This is how HP's proprietary area-wide processing compares with existing popular point processing technologies for building functional parts. In the time it takes these slower point processes to build 1,000 parts, HP's multi-jet fusion technology would have created several thousands of parts. Using HP's proprietary multi-agent printing, The HP multi-jet fusion technology achieves new levels of part quality at these breakthrough speeds.
If we continue our dive into the technology, consider that MGF molds one layer at a time, we see that in each of the layers, we ensure that the part is properly fused to reach out target density and avoid any porosity inside the part. However, this is the easiest part. Historically, one of the weak spots of 3D printing comes when the layers are being built and they are bonded between each other. Normally, the bonding that can be created between layers is not as strong as that fused in. However, as we have the detailing agent, which is acting as a thermal isolator, we can force some intermolecular diffusion between layers, accelerated by the higher temperature when fusing the material. While at the same time, the borders of the part are cooled down to avoid additional material sintering on the lateral surfaces of the part. This intermolecular diffusion is creating a better entanglement between layers, which provides higher mechanical properties in the final part created in the process. The parts printed are almost isotropic depending on the property. For example, for the tensile strength, the behavior is isotropic. However, on the other hand, the elongation in XY and the impact are higher in the XY or horizontal than in the vertical or in the Z direction. So in that case, the behavior is less isotropic. One of the biggest advantages of MGF is that parts behave almost the same in X, Y, and Z, whereas other technologies show some weaknesses in adding Z layers. MGF can achieve almost the same mechanical properties in all directions. For structural parts, where the elongation or impact are not relevant, the orientation of the part in the job is not important, and it does need to be considered during design. However, for snap fits, protection covers, or any other part where elongation and impact are key factors, those variations depending on the printing orientation should be taken into account, and the parts could be designed to optimize the performance and to work around that effect. So concluding, with MGF, you can expect higher densities and almost ideal isotropic properties in all directions, which is a big advantage in cases where you have dynamic and cyclic clouds like prosthetics or orthotics. Very big advantage in MGF for a certain kind of applications. To achieve that, HP have nowadays a range of materials that cover polyamides, TPUs, and polyolefins. Depending on the application, the material should be chosen accordingly. Polyamides offer excellent engineering grade material, and they are HP branded. The main qualities are rigidity, lightness, dimensional accuracy, and water tightness. PA12 is the most balanced material, offering good mechanical properties at affordable economic price. Excellent for most of the applications, is the most used material from HP. P11 is a natural plastic made of castor oil from the resin plant that offers better mechanical properties with higher ductility and higher impact resistance. PA12 glass bits is especially suitable when rigidity and necessary thermal resistance is required. The TPUs available are very similar, but they have different branded, BSF and Lubrizol, and they are designed for different systems. BSF for the MGF 5200 and the Lubrizol for the MGF 4200. The TPUs are characterized by being elastic material with good energy recovery and tear resistance. The hardness can be customizable through design. Soon there will be availability on PP material, offering good chemical resistance, water tightness in a very cheap way. Data sheets on mechanical properties and dimensional accuracy can be found on the HP website. Just to illustrate the mechanical properties of the polyamides, we can take a look into the slide. From the graph, we can see that the PA12 and the P11 are similar in higher tensile strength, but P11 has a higher elongation at break, and therefore it's also higher the impact strength. PA12 glass bits has a higher slope, so it has higher stiffness, giving it a higher tensile models. Important in this segment is the fact that HP materials are certified for biocompatibility. This states that we have performed tests over our powder and our print applications, but that doesn't mean that the end manufacturer doesn't have to make their own certification according to the standards and rules applicable. This is just a statement that according to our tests that replicate most of the tests used in the industry are recognized as being certified. Another recommendation in here is that PA11 rises as a natural candidate for orthotics and prosthetics over time, due to the better mechanical properties, but also because of being a sustainable and eco-friendly material. In my opinion, is a natural choice for these applications. Another important aspect is the fact that if necessary, the parts can be sterilized without any major impact on the mechanical properties, and we have conducted internal studies and tests that prove that. The technology is available in 3 different ways: production machines, MGF 5200 and 4200, special thought for medium and high level productions. Prototyping machines with the MGF 540 and 580 meant to be used specifically on prototyping and development of products. We also have 3DAS, is meant to offer a 3D printing as a service where customers pay for what they print without the weight of capital investment for acquisition. More information on the different options can be found also in the HP webpage. The 3D printing workflow for the MGF 5200 and 4200 series can be resumed in 6 steps. First step is having the parts correctly designed for MGF. CAD or scanning files require the respect of some guidelines and the use of pre-processing software in order to be printable. Generally, pre-processing softwares are required to clean up the generated meshes, and in the market you can find references as Magic, NetFab, or Siemens NX. Pre-process the printing is done by loading the material to the build unit in the post-processing station. A third step involves printing. The building is inserted into the printer, and the files are exported to the printer also. Post-processing the parts means that when you take the building unit from the printer, you're gonna make it cool it for around 40 hours if is a natural cooling. And then the building unit will be inserted to the post-processing unit where you reclaim the non-used powder and you collect the parts. After collecting the parts, they need to be cleaned from the crust and fused powder attached to them, and bead blasting, water jetting, and dry ice are the more common methods. A secondary post-processing can be applied in order to improve surface finishing, and several methods can be used like tumbling, CNC machining, chemical polish can be used. You can also apply color, and the most common methods are dyeing or painting the parts. For the 500 series, the process is similar, but the pre-processing, the printing, and the post-processing steps are all in the same machine. The 580 color machine, of course, do not need dyeing or painting to make color parts. Regarding the design workflow to prepare the geometries, I'm going to be very brief, but basically you have several levels in the industry. You have the basic, the advanced, or the end-to-end. Basically, these are what the industry uses to produce the geometries to be printed. And the most common and the basic usage until now is being done with Vorum or Rodin 4D, where after having the scan, you work one by one the geometries in a technical way done by the designer. In a more high-end usage, advanced, you have several softwares like CAD softwares like SolidWorks or Rhino that have algorithms that are enabled to create automatically meshes or textures that help to improve and make a faster iteration over the design. However, this advance still requires an expert designer to manipulate these 3D files. However, we've been seeing in the latest years that these startups are bringing more and more end-to-end solutions based on software algorithms that simplify all the process and make the workflow in one single stage. Basically, you scan your feet or your body part that needs the orthotics or the prosthetics, and everything will be done through algorithm that will provide the 3D file in the end ready to be printed. But just to illustrate the most common way of doing this, in this case is made with SolidWorks and Mesh Mixer, that is a free software to handle mesh files. And basically from the beginning, you start with the scan file, you create a thickness over that structures that replicate the geometry, and then you make several iterations in order to make it adaptable and making it printable. At this stage, you can, if you have the capabilities of finite element analysis, make analysis over the requirements of the part by introducing the biodynamics and biodata provided by the clinician. Several stages of complexity can be added in here, but this is just to give an idea of how the workflows might work. Once you have the parts to be printed, basically you need to nest them in the job, and just to have an idea of the values and the size of the parts and the volume that you can print. You can see in the slide that basically with the 500 series you can print 16 liters. Of course, this is the total useful volume. And with the 5000 series and 4000 series, you can go up to 41 liters of build volume in the chamber. Regarding the production times, we have 20 hours for the 500 series with all process in one, and then you start to see a faster capability to print full jobs with the 4200 series around 16 hours and 5200 series 12 hours. As final process, just to illustrate that you can post-processing the parts. Most of the time they are to be used in a daily basis, and the post-processing is required not only for comfort but also for the static of the parts. So most of the time dyeing and painting can be the most common solutions to finish the parts. As you can see in the chart, HP offers a range of solutions for prototyping to high production with different levels of service and support. We now start a new chapter in this presentation dealing with the customer success stories, and in here we can see the quality and the capacities and the improvements done by the industry by using MGF in their applications. I will start by the install customer use cases, and in here I will start by mentioning Eventual Medic. Eventual Medic is a high-tech medical startup company that specializes in research and development, advanced technology, and clinic equipment. They focus on synergy of cutting-edge technology with the human touch to produce personal wearables. The challenge of their applications traditionally is that you need to use subtractive manufacturing processes to make insoles. And as we know, the waste, the human factor is very high, and as a startup company, they are in that model of business that I explained before. From their inception, Eventual Medical planned to change how this type of devices are designed and made. The plan was to leverage 3D scanning software and 3D printing to simplify and streamline the process. In the past, however, 3D printing technology was too limiting. The materials were inadequate, the machines were too slow, and they didn't offer the mechanical properties that Eventual Medical needed to fully execute their vision. Working with HP, Eventual Medical spent a significant amount of time and energy developing its products, including orthotic insoles, ankle-foot orthoses, cranial helmets, and protective face masks, among others. Once the products were designed, they were conduct rigorous testing to ensure the products would perform as needed. Their solution includes a software tool that allows podiatrists and other medical professions to quickly design and order each pair of custom orthotics. First, the patient foot is designed in a 2D scan, and then the clinician uses Inventor Medic configurator tool where they can choose and customize their product. I will leave you now with a video of their application that illustrates in a more clear way.
I started working out with personal coach and I started noticing some pain in my feet.
With interactive configurator and 3D printing technology, I am able to design truly custom, perfectly fitting orthotic insoles.
With multi-jet fusion technology, we are able to design and print out directly the final product to make the product lighter, more comfortable, flexible, and to higher its performance.
After I got my first insoles, I was really surprised because I was able to run almost for an hour without noticing any pain. I can fit them into any of my shoes and don't even notice them.
We believe that with 3D printing by HP, we can disrupt the whole industry by providing patients all around the globe with new advanced products that can improve their lives.
As a customer success story in prosthetics and orthotics, I will start by introducing Ulutech, that is a full-service 3D printing company based in Netherlands. Although founded in 2015, Ulutech has more than 15 years of experience and technical knowledge in defense, security, and medical production industries. A prosthetic leg socket serves as an interface between the residuum, the part of the body that is underwent in surgery, and the prosthesis, ideally allowing comfortable weight bearing and movement control. To create a conventional socket, the product is typically handmade with plaster, like we already seen, which results in a heavy weight, poor durability, and a lack of comfort for the patients, in addition to a long production lead time. Therefore, Ulutech began to explore new 3D printing technologies to simplify and transform their production process. The HP solution brings to Ulutech speed in making their parts, creating a uniquely competitive advantage. With a prosthetic socket, for example, the traditional process could take weeks or even months to make, but parts produced with HP multi-jet fusion could be manufactured and delivered to the customers in just a few days. I will now let you with a video with the words from the customer and the user of prosthetics to better illustrate how big are the advantages in using 3D printing.
I had an amputation when I was 1 year old, and so since then I've had so many prosthetic legs.
My patient lost his leg when a traumatic accident, and he came with a wish to walk again. So we make a socket as an interface for his prosthetic foot.
What HP has solved for us is the quality of the products.
Unlike previous experiences I had, that I had to fit the socket a couple of times, could take sometimes weeks, in some cases months to get the final fit. This one was perfect fit the first time.
Main reason Ulutech invested in this new MGF technology was the fast production time of parts. Today the order, tomorrow they will use it on their patient.
I believe that this technology is a good step towards future when we as patients can get the results very quick and see that we can comfortably go back to life without waiting and sitting until the solutions are ready.
Another great example, in my opinion, is ProsFit, They are an international leader in providing below-knee 3D printing prosthetic sockets. Their quality-assured industrial solutions provide clinics all over the world with the latest technology to create robust and reliable prosthetic sockets for the world's more than 10 million amputees. Leg prosthetics typically feature two main elements, the socket and the customized for each residual limb, while the other components such as the foot, knee, and connecting elements are industrial produced standard catalog items. Recently, sockets for prosthetic limbs were made using a plaster mold, after which a patient would need to participate in several checks and fittings that could take weeks or extra appointments with clinicians. ProsFit's previous manufacturing methods were time-consuming and did not guarantee consistency over the output, with an estimated 2 out of every 10 sockets failing. By digitalizing the process of designing, fitting, and manufacturing a prosthetic socket, ProsFit has reduced the time it takes to make and deliver a socket from weeks to days. There are far few steps which help us lower the cost and improve convenience for their patients. The final socket can now be made and fitted in only 2 visits. Because of HP multi-jet fusion technology, ProsFit can now choose how products are manufactured. In the past, with FDM, they were limited to vertical production, but with HP multi-jet fusion, they can choose the orientation that provides the best combination of quality, strength, flexibility, and economics. The resulting product is less costly and more comfortable for the patients. I will let you now with what I think is an impressive story from one of the founders of this company that really brings clear the capacities and the advantages of printing sockets.
ProsFit is the first company in the prosthetics industry to have developed a fully digital solution for the design and manufacturing of prosthetic sockets. One of the other things that makes us unique is one of the co-founders, my son Christopher. He is himself a double lower limb amputee.
In 2009 I was involved in an accident, and as a result of that I had both my legs amputated. So since then I've had a need for prosthetic sockets and prostheses to be mobile. The prosthetic sockets that you get usually tend to be very heavy, quite rigid pieces, and they're not always that comfortable to walk on. And it's a big problem for a lot of amputees that they're basically permanently in pain when they're walking. The prosthetics industry was living within a world of certain limitations. ProsFit entered the game and said, okay, forget all the limitations, we have new ideas. At ProsFit, we have a very particular challenge, and that's that the products that we are supplying are custom made for each individual, and 3D printing is absolutely perfect for that. With HP's MJF today, we are producing sockets, and I'm wearing a prototype example right now.
We see the role of HP as being very strong within the industry. We apply it to prosthetics. It can equally be applied to orthotics, braces, exoskeletons, even to dentistry. And for us, it's a great company because, you know, we basically want to fit amputees in all corners of the world, and having access to that equipment that we know is consistent and high quality everywhere we go is going to be very strong.
Another great example is Crispin Orthotics. They create orthotic devices that can prevent, correct, and deliver relief for symptoms of several injuries. Each patient individual condition requires an individual solution, which is why their orthotics service covers everything from assessment and fitting to aftercare. Crispin works with the National Health System and private patients throughout the United Kingdom. An ankle foot orthosis is primarily designed for individuals who have a neurologic condition such as multiple sclerosis or complications arising from a cerebrovascular accident, which affects muscle control in the lower limbs, particularly in the dorsiflexion muscles. Within the orthotics industry, it's not possible to create a dynamic ankle foot orthosis without using carbon fiber. Carbon fiber is not adjustable, not environmentally friendly, difficult to finish, and very expensive to produce. The HP solution brings that Crispin replaces carbon fiber with HP 3D high reusability PA12, and with that they create a design that was unique with weight reduction and that could answer to the requirements of their parts. They assume that they reduce the costs in more than 50% and they improve the cosmetics and the lightness of the parts. I will let you now with a video of Crispin, another great example of the applications in the segment.
Crispin Orthotics provides an orthotic service and products to the National Health Service and to private patients. The industry for orthotics tends to be quite traditional in manufacturing. What we decided to do was look at various types of technology that we could implement to try and improve the products and make them more accurate. These products tend to be insoles, knee braces, wrist supports, back supports, collars. 3D printing allows the creation of products that we've not been able to manufacture previously.
The HP machine is streets ahead of what we've had before. It actually allows you to produce completely different devices that will give the same, if not better performance with better patient outcomes.
We can use a type of materials which we've not had access to. It also allows us to use fairly complex geometries, which we can then develop new products for the patients that are more effective and can be more cosmetic.
The fact that we can make them much more minimal but keeping the same strength, so we can create much more modern looking things, stronger things, but reducing the bulk and generally improving cosmesis in people's lives.
Everything we do is quite unique. I think at the moment we're probably doing maybe 50 or so devices per week.
We can literally manufacture anything. It has been nothing short of a real eye-opener. I think in 12 months' time we'll be doing things that even now we have no idea that we can manufacture. It really is that revolutionary in the orthotics industry.
And to finalize, I would like to bring you another amazing case from Invental Medical that, as I already stated, is a high-tech medical startup company. Cranial remolding orthosis is the only effective treatment for a very severe head-shape deformities, which occur in 1 to 2% of the newborns. Invental Medical clinically tests baby helmet called Tally. It's designed to correct such cranial deformities. These helmets are traditionally made by milling a mold from polyurethane foam and draping thermoplastic around the mold, a process that is both time-consuming and difficult to scale. Invental Medical turned to 3D scanning, software, and 3D printing, especially HP multi-jet fusion technology, to simplify this streamline and the process. The 3D printing custom-made version of this baby helmet delivers gentle, effective orthotic treatment while providing enhancement in the comfort thanks to its lighter weight. It's also equipped with a unique bioresponsive structure and a sensor to improve the treatment success rate. Producing functional parts with HP multi-jet fusion technology also helps them to deliver a high-quality output with 10 times faster time to market and at half cost. As you can see in this picture, the design was so inventive that in the interior part, they use a adaptable mesh that, by using the same material in the outside, in the internal part of the helmet, you can see the difference, because the outside is highly stiff while the inside is adaptable to the shape of the baby. I will leave you now with my last video that shows how MGF can improve the quality of life of many persons and can help customers and patients to have better products that can improve the quality of life.
So this helmet is indicated for patients with craniosynostosis after operation via endoscopic control, and is necessary part of the treatment for this baby.
With multi-jet fusion technology, we are able to design and print out directly the final product. The process is faster and the product is lighter and more comfortable.
3D printed helmet helps us to use a minimally invasive technique for treatment.
With 3D printing by HP, we can disrupt the whole industry by providing patients all around the globe with new advanced products that can improve their lives.
And with this, it's all. I hope you enjoy it and you found useful the information that I share in here. We are now open for questions and answers. Thank you very much for attending.